We have so far seen questions where the wedge is fixed. And so basically when you're looking at a block that slides down like that, it just simply slides down on the wedge. So we know that the block is moving in this direction, right? We have used this very often. Now when you looked at moving pulleys, you had a different kind of constraint equation that we wrote. For a fixed wedge, there is a very different simple constraint. The constraint is that this block is going to move along the incline. So its acceleration is going to be right along this direction, right? In that direction. So if I try to mark it, it will look like this. But what will happen if this incline wedge can also start moving? Okay, now those kinds of questions are a little bit more tricky. Sometimes it may happen that I'm pushing it here so it's moving forward, but sometimes it may happen because of this block. Now this block looks quite small and this looks quite large, but imagine that this was quite light. So then this is pushing this fellow down. There's a normal force in this direction, which means there is a component of normal force horizontally. If this was frictionless, this can start to slide back. Okay, now imagine a situation like that. So watch what I'm going to do now. So I'm going to have this block released. So I'm going to basically get this block started. So let me first show you without moving this wedge. So if I just push it, you can see it's just coming down straight. But now I'm going to do the same thing, but what I'm going to do is as it's moving down, I'm going to also move this. Watch again. So I'm going to make this fellow move and I'm also going to make this wedge move. So can you see that? Let's see it again. So when you see this fellow came here, did not go there. So this block B was moving like this. It doesn't mean it's going into the wedge. It just simply means the wedge position has changed. When the block was there, the wedge was here. When the wedge came here, the block has actually gone to this position. So because the block is moving down and the wedge is moving that way, you can see how it's going, right? So the block can start to move at angles like this, which makes it a little complicated because this one, at least I knew the angle at which it was going. So if I told you that this acceleration was A, this is theta, this is theta. So you know the horizontal acceleration must be A cos theta because this is A cos theta resolution, right? And you know that the vertical acceleration was A sin theta. Now the problem is, because this wedge is moving, okay, so let us say that the wedge moves this way. As it moves, I come down. So this fellow is going like this. I don't know this angle, right? So you need to basically look at the fact that this guy has an acceleration B and this fellow has an acceleration in this direction. So that means this is slightly more messy. So what we are going to do now is to learn how to address questions of this kind. Before we get to this is a little bit complicated. Let us look at a slightly simpler question. Now in this question, you have an inclined wedge. Okay, so wedge itself generally means something like this that can also move. Okay, so this is an inclined wedge and there is a block that is resting on it. But then what are these fellows? These fellows are walls. So there is a wall and through the wall there is a hole. Imagine that there is a floor and you have put a pipe through it. So imagine this situation. So there is a hole. Now this fellow has a hole in it and I'm going to keep this fixed. So this is fixed. This is a rod or a block, whichever way you want to think of it. Now because of this pipe, this is fixed. That means this rod can move up and down, but it cannot move sideways. It cannot do this. It cannot do that. So it can only move vertically. Now the question is, if this fellow is pushing this block, okay, the wedge, inclined wedge, so then what is going to happen? Let's see. So if I keep it this way, then obviously if this wedge doesn't move, the pipe or the rod that you are seeing here won't move. So I'm going to keep this pipe fixed. So that means the rod can only move vertically. So now this block, the inclined wedge, is going to start moving this way. As it starts moving, can you see what is happening? Can you see what's happening? This rod is coming down vertically, and if I start to move this guy horizontally like that, then as it's pushing, there's a lot of friction in this case, but as it's pushing, you can see that this fellow goes up. So let me repeat it. So as I move the wedge this way, you can see that the rod is coming down, but at the same location. Why same location? Because this point is fixed. This thing that is constraining this rod is fixed. So as the inclined wedge moves, the rod just simply comes down, right? So let us try to understand how much will this fellow move if that fellow moves by some amount, or how much will that fellow B move if A moves by some amount. So how will I solve a problem like that? Use a little bit of geometry. So the approach I want you to understand is called dots and lines. Now when you think about blocks and when you think about inclined wedges, our brains don't work very well, because you see, we are more used to in geometry using dots and lines, right? So therefore, remove all of these things and replace them as lines and dots. So what I'm going to do is I will show you here. I will convert this entire thing just into a line, so that way we will be able to understand it much better. So let me pick this up. So what I'm going to do is I'm going to have just this line, okay? And then imagine that there was just one line here. Now in this case already this looks like a line, so it's easy to imagine. But what you should think of is that this is just one single line, okay? And then there is a dot which is basically on this line. Now if this line moves parallel, forget the wedge, don't imagine the wedge, just look at the line. So imagine that this line or the entire wedge has moved parallel to itself like this. So that means this point would have come there, right? And that point would have come here. So this is the amount that has been moved by these points. So focus on dots, focus on lines, because our geometry is entirely lines and dots. Well, if this incline has moved to this position, where do you think this line is going to go? It is going to come down vertically, right? So this point is going to come down vertically here. So how much has this point moved? This much. How much has this line moved? This much, which is basically the point here has moved so much and the point here has moved so much. So how much was the motion of B, this block? This much. How much was the motion of this wedge? That much, right? So what is the connection between B and A? Ideally, you should not even use B and A, you should just use A and you should write B in terms of A, which is what we are going to do now. Okay, so let us try to see what is the connection between A and B. If you took this point on the incline, right? So imagine this, so basically I don't like this line because that line is unnecessarily disturbing us. So let us just erase this line. So can you see this incline? If I had a point on the incline, what would have happened to that point? That point would have moved like this, correct? Now every point on the incline has moved by A. So what is this displacement? A. Can you see that this is A, this is B. Now if this angle is theta, this angle is theta, because these two are parallel lines, and these are transversal. So these are angles which you can see clearly, this angle and that angle must be equal, right? Corresponding angles. And so if this angle is theta, this angle is on the alternate side, so therefore this angle is theta. Well, if this angle is theta, that means B by A must be tan theta, because this is 90 degrees. This is moving horizontally, that is moving vertically. So we can conclude B by A is tan theta. Can you see that? B is the opposite side, A is the adjacent side. So B by A is tan theta, which means B is A tan theta. So if this wedge moves by A, this block on top or the rod on top is going to move down by B, and that's what is going to happen in this case. So if I took this wedge and this block, as I start moving this wedge, this block comes down. If this guy moves by A, that guy goes down by A tan theta. But it's not just for displacement, you already know this for other things. If this fellow had an, let us say, velocity V in this direction, this fellow will have a velocity in this direction which is equal to V tan theta. So if the wedge has a velocity V, the rod or the block, whichever one you want to call it, that is going to have a velocity V tan theta vertically. So this constraint makes sure there is a connection between this and that. How do you figure that out? Because this can only move vertically, this can only move horizontally, but these 2 points have to basically be aligned. So you have to have this point on the incline. It was not always on this point. right? It is somewhere on the incline, which means when the incline comes here vertically below, this is the place where it is. So this block has to go down by B, whereas this fellow has gone by A, and B by A is tan theta. So I hope that is clear. Now that is going to help us solve a lot of other things. So similarly for acceleration, you should be able to do, if this guy has an acceleration A, that fellow will have an acceleration A tan theta. Remember this question that we started out with? So you had this block that was sliding down, but then this wedge was also moving. So when the block is sliding down, it's simple because it's just coming to this location. But if the block starts to slide down and the wedge is also moving, let's see what happens. We saw this already. You see that this guy is going down like that. So that means block B is going this way instead of going like that. But this is a bit messy for us to calculate because I don't know anything about the angle. Okay, so instead what I'm going to do is, let us see if I think of this as physically coming down here and then us moving there. Will that also work? Yes, right? So one option is for us to say this guy is just simply sliding down, and then when it comes here, everything freezes and then you are moving this way. That means you can think of this motion as this motion plus this motion. Right? Now when you're moving horizontally, you're moving because block A, this wedge is moving. Okay? So wedge, basically this triangular wedge is moving this way. And because it is moving that way, you say this fellow comes down, this point is not going to change anymore. Now it is just simply sliding because it's moving, this wedge is sliding, and so this block is just simply moving like that. It is no longer sliding on the incline. So we can, actual motion is this. B, let us say actual. But I'm going to say this is B on the incline plus, what was that? If the wedge was not moving, this is what would have happened. So what is this? This is because the wedge has moved, so I'm going to call that A. Now what is this connection between A and B? Okay, or B actual and A, that's basically what we need to figure out. So let us think again. I am actually going to say this is going to be left. As it's going to come down, you can see this is how it came down. But what I'm interested in is calculating this or writing this in terms of a horizontal and in terms of vertical component. The problem is I don't know this angle because this is not along the incline, this is bent. So B and A. If I use vector notation, I can say B actual vector is B vector on the plane plus A vector. Of course, we don't want to use vectors to do this thing. B vector plus A vector. A is the motion of this incline, right? How do I draw this and figure this out geometrically? So that is the real question. So let me draw it separately. Okay, so I'm going to now take this thing parallel here. So just ignore this side. So let us draw it again. So I have a line that is parallel. So this makes an angle theta. I am not going to complete the wedge. I am only going to deal with lines, dots and lines. And I will make B into a dot. Is that okay? Because our brains can understand dots and lines much better than they can understand actual motion like this. Now this fellow, this incline is going to move this way, right? So it's going to move horizontally like this. So which means this is what is going to be the new position. This is A. This is A. We could have assumed that this fellow first moved like this, then slid down. Like for example, you can say it slid down and then moved this way. But you can also complete a parallelogram and you can say first it moved like this, then it went down. You can see that this must be B. Can you see this is B and that is A? Easy for us to think of. Actual motion was somewhere here. So this is how it actually moved. But what I can do is I can say it moves this much and then comes down like that. It moves like this. And this is A. Can you see? because this point has moved A, this point has moved A, this point has moved A. You can either use this triangle or you can use this triangle. It doesn't matter. Okay, so now what would this be? This is B. What is this? This is also B. Since these two lines are parallel, this must be theta. This must be theta because these two lines are also parallel, right? Now if I look at B and I take its component, look at this length. This is B, and so what is that? That is going to be B cos theta. And this is A. Is that clear? This whole thing, if I draw it like this, you can see it better. This is B cos theta. But this is A. So how much is this? B cos theta minus A. Now that is the horizontal component of this vector. Can you see this vector's horizontal component is B cos theta minus A, because B cos theta is this much and A was this much. So it should have gone B cos theta forward, but then it came back A. You can also do it here, because this angle is theta, that angle is theta. You can say that is B cos theta, and then it came back A. So how much did it go forward? B cos theta minus A, I cap. If I want to use vector notation, I'll say I cap. Okay, so this is B actual. This is the horizontal component. And then there is a vertical component. How much is the vertical component? Well, the vertical component is the same as this vertical component. So this was B cos theta. This is B sin theta. And that is the only amount that is coming down, because this wedge is not moving vertically. It's only moving horizontally. So that means the vertical motion was entirely due to B. So that means plus, or rather minus, because it's going down, B sin theta j cap. This is vector notation, but usually what I will do is I'll go back to this block and I'll say, well, the block has a horizontal acceleration, not B, but I'll say B cos theta minus A, and the block has a vertical acceleration, B sin theta, where B is this. But the assumption itself, now I have only two variables, think of it. Otherwise I would have had to have a Bx and a By and an A, which would have made it 3 variables. Now I have an A and I have only one B. And I have written both of these accelerations in terms of A and B. So look at that. There is a combination of A and B. There is a combination of B here. So that means both accelerations we found using 2 variables. So when you look at Newton's laws, you will be specified how many variables you need, right? So suppose you are only allowed 2 variables. I can write both these accelerations in terms of 2 variables, in spite of the fact that this fellow is going down at some weird angle. So is that hopefully clear? So the idea is to convert all inclined surfaces into lines and all blocks into dots, so that you can then use a lot of geometry to figure out what is the connection between the lines movement and the dots movement.